What's up, everyone? This is LeetCode 310, minimum height trees. I'm going to summarize the problem because I don't want to read all this. You can read it for yourself. But basically, you're just giving a tree, right, with no cycles or anything. And you basically have to pick the node and return the node, which gives you the tree with the minimum height. Meaning, any of these nodes you can pick as a root, and you have to pick the root, which gives you the minimum height in the tree, right? We're going to go to an example kind of to illustrate how we're going to approach this problem, right? How do we pick the node that gives us the minimum root? Okay. And the idea really is to think of the approach to this problem kind of like an onion, right? Onions, you peel out the outer layer. In this problem, it's going to be kind of similar. Because we're at every iteration in kind of our approach, we're going to remove the leaves. What are leaves? They're just basically nodes which only have one connection, right? Or one edge, I should say. Okay. So at every step, we remove all the leaves, right? Kind of like an onion. Okay. Now we're left with this. Next step, we're going to do the same. Boom. Okay, and this is our answer. Now, how do we know when to stop? Basically, when we have one or two nodes, right? And the reason it has to be one or two is because you could have cases like this, right? Right. Let's do the same process. Let's remove all the outer leaves, or not outer leaves because the leaves are on the outside of the or on the outer part of the tree. But let's remove all the leaves at every step. Okay, so step or at the first iteration. So at the first iteration, let's remove all the leaves. Boom. Now we're left with this. Well, we can't really remove this 3 and this 4. We'd be left with nothing, right? So there are cases like this where you might have two nodes left. So before you begin an iteration, you want to check, do I have less than or equal to 2 nodes left to process? If so, then we actually want to stop there and just return, okay? Because you can see, even if we pick the 4, we have the same issue, right? We do this, we do this, we do this, and we're left with this, right? So there's not one node in particular we can pick. We have 2, okay? That's kind of the approach to the problem, because we basically remove the leaves layer by layer, because the leaves are just the farthest nodes, right? That's all they are. So when we remove them repeatedly, we're kind of shrinking the tree towards the center of the longest path, which is exactly where the root should be to kind of minimize the height, as you can see by the picture that I drew, right? So first of all, let's handle an edge case, which many of these problems have edge cases, right? So if n is equal to 1, we just return 0, right? Because if we only have one node, the height is just 0, right? Okay. Now, now in terms of how we're going to approach this problem, first of all, we have to set up our kind of our graph. So we have to build our adjacency list, right? So we're just going to say adjacency list is default dict list. Degree is going to be equal to 0. And remember, our degree really is just how many connections does a particular node have, and then the adjacency list is basically us linking the edges together. If in case you haven't done a tree problem in a while, that's really all this is doing, right? So the adjacency list for A, right, we want to append B, right? So basically, we're just adding edge. We're adding edge A, mapping it to B. We're basically doing the same for B, right? Dot append A. We're basically adding the edge B and mapping that to A. And then degree of A plus equal 1, right? B. The degree really is like just the amount of connections, right? Because let me go up. So when we're doing this, right, we're mapping, this is B and this is A. The degree is 1 and the degree is 1. But let's say B has to map to C. When we map this, the degree is 1, and now we add 1 to the degree, and the degree is 2, right? It makes sense because B goes to A and it also goes to C, so B has 2 connections. Okay, and we obviously need that information as for our algorithm, right? So here's just kind of simple stuff, just basic graph stuff. We're just building out our adjacency list. Now, in terms of how we're going to process these leaves, you know, in terms of quote unquote the iteration, is we're just going to use a queue, okay? And at every step, so it's kind of like well, we've done tree problems in the past where we've used a queue to kind of process certain nodes at a particular level. It's kind of the same concept, but rather than processing a particular level, because this tree can be structured in many different ways, we're really just what we're really doing at a particular quote unquote level, which is not a level, it's just an iteration, is we're processing all the leaves at a particular point in time, right? Then the next time we're going to process a new set of leaves, right? Because the tree should be smaller. Okay. So make a double-ended queue. Okay. Now here we're basically going to find the leaves and just find the leaves and basically just append to the queue. Okay. We're going to say for I in range of n, we're going to say if the degree of I is equal to 1, meaning it's a leaf node, right? Because it only has one connection. So really it should be at the very outside part of the graph. Because if there's only one connection, it is just a leaf node, right? So if degree of I is just 1, we know it's a leaf, so we're going to say leaves.append, and leaves is just our queue, right? Leaves.append I, okay? And remaining, oops, this goes out here. And the remaining nodes is equal to n, right? We need remaining nodes because that's basically going to let us know when we should stop, right? When we have less than or equal to 2 nodes. Okay. So we're going to say while remaining nodes is greater than 2, while remaining nodes is greater than 2, we can just keep going, right? We can keep going. And this is basically where our actual quote-unquote algorithm is going to happen, right? And I will comment some stuff just so you're not too lost. So basically we're going to say we're going to handle the current layer of leaves, right? So decrement the remaining nodes by leaf count, right? Because initially, let's say we have n nodes, right, in our graph. Like, let's say we're processing this, right? We have 1, 2, 3, 4 nodes. Well, in our leaf, we're currently processing 3 leaf nodes. So we're going to take 4 minus 3, and we should have 1 node left over. So after our first iteration, we know we should stop because this while loop will not be true anymore, right? So all this is doing is basically saying, hey, let's take the remaining nodes that we had previously and decrement the amount by the amount of the leaves that we're currently processing. And that's basically the amount of remaining nodes that we'll have left over, right? Just basic stuff. Okay. I'm going to say leaf count is going to be the length of leaves, right? And then remaining nodes is going to be just minus equals leaf count. I know I could put this all in one line, but I'm just writing it like this so it's easier to understand, right? I'm going to say next, we're going to have to peel off the outer layer of leaves, right? Right? And then we have to update the degree of the neighbor of the leaves since the leaf is removed. What does that mean, right? Like, let me go like this. So the degree right now for C is 1. The degree for B is 2. Okay? When we process this, when we process this, we remove it, right? Because these are leaf nodes. That means every time we remove a leaf, this has to get basically, the degree has to get updated, right? Because if we're only looking at this now, the degree is not 2, it should be 1, right? Because we only have this, right? So we need, every time we remove a leaf, we need to basically update the degree for its neighbor because this leaf is not going to be a part of the tree anymore, right? So we need to make sure we do that, right? And basically, if the degree of the neighbor is equal to 1, append it to the queue because it's a leaf, right? Go back to my picture here. Let me just draw something else. So if we have like an A points to another node that's a B, and this points to a C, right? And this points to a D, and this points to, I don't know, an F or something, right? Let's say we remove this F, right? So the degree for this D here is obviously 2 because it has, I shouldn't draw the arrows actually because it is bidirectional because they're just edges, right? So maybe I shouldn't do that, sorry. I don't want to confuse you. But so the degree for this D is 2, right? Because it has 2 connections to B and to F. Well, when we remove this F, we want to update the degree here. So this is 1. But because the degree is 1 now, we know that this D is basically a leaf node, right? Because it only has one connection. So this is a new leaf, so we actually want to append it to the queue, right? We want to, that's not a node, that's supposed to be queue, sorry. I know I'm being confusing. But basically, the connection, or the degree for this D node is 1, so it's a leaf, so let's basically just add it to the queue, okay? Because we can actually process it now because it's a leaf. So the next iteration, this D will be in the queue, and we will process it accordingly. So that's kind of how we shrink our tree accordingly. Okay, it's basically our step. It's not too complicated, really, to understand what we're doing. Okay, we're going to say leaf is equal to leaves.popleft, right? So we're basically going to check the neighbors for the leaf. So we're going to say for neighbor and adjacency list of the leaf, right? We want to decrease the degree for that particular neighbor by 1, right? Because this leaf is going to go away, or removing it from the tree, basically. And basically, if the degree of that neighbor is equals to 1 now, that basically means it's a leaf, so we can do leaves.append leaves.append neighbor. Okay. And I believe that should be it. And then when we're done here, when we stop the while loop, the remaining nodes really will just be in the leaves, meaning it'll be in the queue, so we can just return a list of leaves, okay? And that should be it. But yeah, this problem is a little bit tricky. I hope my explanation was at least somewhat clear, because this problem definitely is a little tricky, and honestly, there are a lot of videos on this problem, but I don't think a lot of them are very clear, so I tried to make mine as best I can. I hope this helped. But yeah, this is just the code. I hope it helped you, and I'll see you in the next one. Peace out.